Now in this session, we will discuss about the practical or the experimental procedures, observation and calculations of shell and tube heat exchanger. So the main objective of this shell and tube heat exchanger to calculate the overall heat transfer coefficient. So we have discussed about the heat transfer coefficient, then the different types of heat exchangers. Under that, one of the commonest example is shell and tube heat exchanger. The relevant program outcomes for this shell and tube heat exchanger is we have to apply the basic knowledge of mathematics, science and engineering. Then we have to apply the discipline knowledge, then experiment and practices skills, engineering tools, and we have to do the experiment or this work in a team. The competency and practical skill is use heat transfer principles to increase efficiency and to save energy in chemical process plants. So for the observations and calculation part, to calculate the overall heat transfer coefficient, we have to measure the temperatures with the help of thermocouples or RTD, whatever available in that experimental setup. Then we have to measure the volumetric flow rate with the help of rotameters. The course outcome for this practical is apply the concept of convection to operate the heat exchangers. So in this shell and tube heat exchanger, we are going to use water. So that is nothing but a liquid, and that is why convection concept is there. So choose proper heat transfer equipment for given applications. So now we have choose the shell and tube heat exchanger for heating of water with the help of hot water only. Then practical outcome, using shell and tube heat exchanger, we have to calculate the overall heat transfer coefficient, that is capital U. The relevant affective domain related to outcome is follow the safe practices, maintain tools and equipments, practice energy conservations, demonstrate working as a leader or a team member. The minimum theoretical background for this shell and tube heat exchanger is, from this diagram you can understand what exactly the shell and tube heat exchanger is. So this is the part of the shell and tube, that is main part is shell and the second is tube. So this is the shell side. So this part is called as shell. This is the shell, and in the shell there are number of tubes. So the tubes, here it is indicated. These are the tubes where one of the liquid is passes through the tubes and other liquid is going to pass from outside the tubes. Now if you observe carefully, there are different types of parts in the shell and tube heat exchanger. Here it is a channel. So this area is called as channel, where we can pass the tube side fluid through this channel. So with the help of these nozzles, we can pass the tube side fluid, and with the help of these nozzles, we can pass the shell side fluid, right? So channel, then channel cover, these tube sheets are the various parts of this shell and tube heat exchanger. So this is the tube sheet. Why it is called as tube sheets? Because in this sheet these tubes are inserted. That is why it is called as tube sheet. This is the part that is called a channel, and that is why this part or this sheet is called a channel cover. Now there are different baffles incorporated in the shell and tube heat exchanger. So we can show these baffles. So this part is baffle, this part is baffle. Now if you observe why these baffles are arranged in a such way, so we can understand. If the shell side fluid is passing from the top, and if it is passing through the shell and going towards the bottom side nozzle, then the movement is like this. Right? So to get this movement, we have to arrange these baffles, which are nothing but a 75% segmental baffle, or it is also called as 25% cut segmental baffle. So why it is called as 25% cut or 75%? Because these baffles in the two-dimensional view, it is like a rod, but actual it is a circular plate, and 25% part of this circular plate is cut. That is why it is called as 25% cut segmental baffle, right? And this 25% cut part is arranged in the shell in a such way that this shell side fluid can pass through that space, right? So the tube side fluid is going to pass from the channel, and we can pass this tube side fluid more than once along the length of heat exchanger with the help of pass partition. So this part is called as pass partition, right? So this is the pass partition, that is nothing but a metallic plate incorporated in the channel for moving or guiding the tube side fluid in this way. So it is going through the shell and tube heat exchanger and then comes out from the nozzle's outlet, that is tube side nozzle outlet, right? So if one metal partition is incorporated on the channel side for the tube side fluid, then this tube side fluid is passing along the length of heat exchanger twice, and then it is called as 1-2 shell and tube heat exchanger, because the shell side fluid is going to pass only once through this heat exchanger in this way, and the tube side fluid is going to pass along this shell and tube heat exchanger twice. So 1-2 means 1 indicates the shell side fluid pass, that is the length of that fluid particle or molecules along the length of heat exchanger. So if it is going to pass only once, then the first number indicates the shell side fluid, and 1-2. So that second number indicates the two passes of the tube side. So the first number indicates the shell side fluid passes, and second number indicates the tube side fluid passes. So in this way, we can add the number of passes by adding the pass partitions. So that may be a 2-4 case, that may be a 2-6 case, or likewise. So on the basis of our application and the requirement, we can add the pass partitions and we can change the shell and tube heat exchanger working in a faster way. Then this is another side of this heat exchanger. So it is also a channel. So this channel is provided for passing this tube side fluid in this way, right? And again, there is a channel cover. Then there may be tie rods for supporting these tubes if the number of tubes are more or if the length of tubes are more. So we can add some other parts for supporting the different parts like tubes, baffles, etc. Right? So this is the construction of this shell and tube heat exchanger, and in this way the heat transfer is working in this shell and tube heat exchanger. So we can understand from this diagram and explanation what is the construction and working of this shell and tube heat exchanger. Because in the actual experimental setup, there is a insulation and aluminum sheet covering. That is why we can't understand what exactly the happening in the inside of this shell and tube heat exchanger. That is why this construction and working part is very important. So from the other diagram also you can understand how this shell and tube heat exchanger is working, right? So this is the shell inlet, these are the baffles. So the baffles are arranged in a such a way that the shell side fluid can pass in this direction, right? Then the tube side fluid inlet is from the bottom side, and these openings of these tubes, so through these openings this tube side fluid is going to pass, right? So this is 1-1, that is normal shell and tube heat exchanger, where this tube side fluid is passing along the shell and tube heat exchanger only once. In the same way, this shell side fluid is also passing through this shell and tube heat exchanger only once, and that is why it is called as 1-1 shell and tube heat exchanger. In the previous diagram, there is pass partition, and that is why the tube side fluid passes 2 times or twice in a shell and tube heat exchanger, and that is why this previous diagram shows the 1-2 shell and tube heat exchanger. So due to this pass partition, this tube side fluid is passing through this shell and tube heat exchanger along the length of heat exchanger twice, and that is why it is 1-2 shell and tube heat exchanger. So we are going to conduct an experiment in the 1-2 shell and tube heat exchanger, right? So this is the experimental setup. The experimental setup may be changed a little bit, but normally it is like that only. This is the shell part and aluminum sheets, and under this aluminum sheets insulation is provided, and that is why we can't understand what exactly the different parts of the shell and tube heat exchanger internally. So we have to understand from the schematic diagrams or the different diagrams or animated diagrams, and with the help of that only we can understand how these shell side fluid and tube side fluid are passing, how the heat transfer is going. Then these are the 2 rotameters for measuring the volumetric flow rate of shell side fluid and tube side fluid. This is the knob arrangement for starting the heaters. This is the digital display where we can observe the different temperatures with the help of different RTDs which are located at inlets and outlets of the nozzles. That is for shell side fluid inlet outlet and for tube side fluid inlet outlet. So from this experimental setup, we can understand how to operate these shell and tube heat exchanger. Now, what are the resources required for this experimental setup? So we require tubes. So in the experimental setup where we are going to conduct this experiment, there are 24 tubes involved under this shell. Then only one shell is there. So the tubes Material of construction is stainless steel. The internal diameter is 13 mm. The outside diameter is 16 mm. The length of tube is 500 mm. So there are 24 tubes involved in the shell and tube heat exchanger assembly, where the ID and OD is 13 and 16 mm and the length of tube is 500 mm. Then the shell is also made up of stainless steel, where the ID is 220 mm and length is 500 mm. Then 25% cut baffle, that is 4 number, 4 baffles are available having 100 mm distance between these baffles. That is nothing but a baffle clearance. So 100 mm is the baffle clearance. So there is a distance between these 4 baffles, that is 100 mm. Then there are 2 rotameters for measuring the volumetric flow rate of shell side and tube side fluid, that is hot fluid and cold fluid. Now we are using the water, that is why it is hot water inlet flow rate and outlet flow rate and cold water inlet and outlet flow rate. So this is approximately maximum limit is 250 LPH. Normally we are going to conduct this experiment near about 150 LPH. Then the precautionary measures are adjust the flow rate properly and consider the reading corresponding to reading age of the float. Wait for the float to be stable before taking and reading. So we have to decide, we have to adjust the volumetric flow rate. As discussed that we are going to conduct this experiment with the help of volumetric flow rate near about 150 LPH. So after stabilizing that float, then and then only we are going to take the readings. Wait for steady state conditions to reach before taking the inlet and outlet temperatures. So before taking the observations, before starting the note down of the observations, that is nothing but the inlet and outlet temperatures of hot and cold water, we have to confirm that steady state temperature is reached. So steady state temperature is nothing but that temperature is not going to change with respect to time. Then what is the procedure to conduct this experiment? Make the cold water to flow through shell side. So shell side fluid is nothing but the cold water, right? Then allow hot water to flow through tube side fluid. So tube side fluid is nothing but the hot water. By opening the valves, then adjust the flow rates of both fluids by adjusting the valves. Then switch on the heater and wait for steady state condition to be attained. Measure the flow rate of hot and cold water with the help of rotameter. Note down the readings of inlet and outlet temperatures of hot and cold water after attaining the steady state temperature condition only. Repeat the procedure for different flow rates of cold water. So this is the simple process. We have to open the valves so that this hot water and cold water can pass through the tube side and shell side respectively. Then we can measure the flow rate of hot and cold water with the help of rotameter. We have to wait for the stabilizing of that float at a particular flow rate, and then we can wait for the steady state temperature, and after reaching the steady state temperature, we can note down the inlet and outlet temperatures of hot and cold water. If required, we can change the volumetric flow rate with the help of rotameter, and we can observe what exactly the effect of this volumetric flow rate on the temperatures and on the overall heat transfer coefficient indirectly. So we can repeat the procedure by changing the flow rate, and we can observe the effects of this change in the volumetric flow rate on the temperatures as well as on the overall heat transfer coefficient value. Then whatever the resources we are going to use, that should be written here in this table. In the above table, these are the suggested specifications of that resources. Now we must have the tubes, shells, baffles and rotameters. So whatever the experimental setup you have, that specification should be noted down in these resources used. Then we have discussed about the procedure to be followed. So whatever the procedure, that is actual procedure, is followed by the students and staff, that should be written here. Then we have discussed about the precautions or precautionary measures before starting or while conducting the experiment. So whatever the actual precautions is followed in the experimental setup, that should be written in this point. Then we have to note down the actual inner diameter of inner pipe, outer diameter of inner pipe, length of pipe, number of tubes. So the experimental setup, whatever we have, that numbers I have already mentioned. That is, inner diameter of inner pipe is 13 mm, outer diameter of inner pipe is 16 mm, length of pipe is 500 mm, and number of tubes are 24 mm. The cold water and hot water flow rates and temperatures we have to note down in this case. Now we have adjusted the flow rate of cold water and hot water as 150 LPH, and it is should be converted into liters per second, and we have to note down the actual temperatures of inlet and outlets of cold water and hot water after the observations in the actual experimental. So we have decided that the volumetric flow rate should be 150 LPH. Then for the calculation purpose, we must know the properties of water, as we are using the water from both the side, that is hot water and cold water. So the specific heat value is 4.187 kilojoules per kgK for hot and cold. Then density of hot and cold is approximate 1000 kg per meter cube. This may be a different value, that is a little bit change, but we have taken the approximate value, that is Cp and density for hot and cold water one and the same. Then mass flow rate. So we have to calculate this mass flow rate. Now we have set the volumetric flow rate as 150 LPH. We know the density of water is 1000 kg per meter cube, and we have to convert this meter cube, a liter into meter cube. So this volumetric flow rate, that rotameter is in terms of LPH. That is why this liter should be converted into meter cube, and this hour should be converted into seconds. So to convert this liter into meter cube, we have to multiply by 10 raised to minus 3. That is the conversion factor. And for converting these hours into seconds, we have to divide these parameter by 3600, right? So we can get this mass flow rate of hot water in terms of kg per second. Then we can calculate the rate of heat transfer, that is Q of hot fluid, with the help of formula, that is mCp delta T. So this is mH into Cph into delta T, that is nothing but the range of hot fluid, Thi minus Tho, because the initial temperature of hot fluid is always greater, and after elimination or removing the energy from the hot water, this temperature is going to decrease, right? So we can write this mass flow rate in terms of kg per second. We can write this Cp value in terms of kilojoules per kgK, and we can write this temperature difference after getting or after conducting the experiment, right? So on the basis of this temperature observation, we can calculate the Q value in terms of watt, that is in terms of joules per second. Now in the similar way, we can calculate the rate of heat transfer for the cold fluid. that is with the help of MCP delta T calculations. So mass flow rate of cold fluid, CP of cold fluid, and temperature difference of cold fluid. So we can find out the mass flow rate of the cold fluid with the help of volumetric flow rate into density, and CP is one and the same, that is 4.187 kilojoules per kgK, and we can find out or we can observe these temperatures while conducting the experiment after reaching the steady state. So this Q can be calculated in terms of watt also. Now the QH and QC average gives you the average rate of heat transfer for this shell and tube heat exchanger. So QH plus QC divided by 2, that gives you the actual rate of heat transfer or the average rate of heat transfer for this shell and tube heat exchanger assembly. Now after calculating this Q, our main aim is to calculate this U, right? So to calculate this U, we must know Q. So we can calculate this Q in this way by step 1, 2, 3, 4. Then we can calculate this area with the help of diameters. We know the diameters, and with the help of delta TLM formula, we can calculate this value, that is log mean temperature difference. So this LMTD is nothing but the difference between these approaches divided by the ln ratio of this difference of temperatures, right? So we can calculate this LMTD value, and then we can put this delta TLM value, A value, and Q value in this formula, and on the basis of this parameter we can calculate the capital U, that is overall heat transfer coefficient. So that is our aim. So this is the area calculation, that is pi dl. Now the number of tubes are 24, that is why we have to multiply this area into 24 to get the overall heat transfer area, because this pi dl calculation only has the area of a single tube. Now there are 24 tubes, that is why we have to multiply this area by 24. Now the outside area, that is again pi dl, but into 24, because 24 numbers of tubes are there. Then we can put these values in this formula and we can get the capital U. In a similar way, we can get the capital UI. So UO and UI can be calculated with the help of same formula, that is Q equal to UA delta TLM. So we have to calculate the area for inside to calculate the UI. We have to calculate the area for outside to calculate UO. And in this way, we can calculate the overall heat transfer coefficient of this shell and tube heat exchanger with the help of different parameters like rate of heat transfer, area of shell and tube heat exchanger, and log mean temperature difference of shell and tube heat exchangers. So we can put these values in this result table, and we can write the final result as UO is equal to this, UI equal to this in terms of watt per meter square Kelvin. So on the basis of this UO and UI value, we can interpret the result and we can conclude why these results are in this way, right? So with the help of this experimental setup, while conducting the experiment, whatever the skills, whatever the knowledge we have applied, we have to check this knowledge and skills with the help of some practical related questions, like give the advantages of shell and tube heat exchanger, define tube pitch, baffle pitch, through which side of shell and tube heat exchanger the following liquids are directed, give reason also, that is corrosive liquid if there is a corrosive liquid, if there is a viscous liquid, if there is a high pressure liquid, then from which side, that is from shell side or from the tube side, this corrosive or viscous or high pressure liquid should be passed. And if that is the case, or it is the answer that this should be passed through this corrosive liquid should be passed through the tube side, then you have to justify with the reason why it is so. Give the uses of these baffles and shell and tube heat exchanger. So with the help of these different types of questions, we can check or verify the knowledge and skills, whatever we have adopted in the or while conducting the experiment. Thank you.